So today we are going to talk about the basic concepts of remote sensing, GIS and GPS, and we'll talk in terms of the image analysis, that is in light of image analysis of remote sensing, GIS and GPS, because ultimately the crux of all this technology is the data and of course the information out of that data. Remote sensing deals with the images, means it senses in various electromagnetic spectrum, right from the visible to the IR, far IR region it takes. So there is a wide region where the sensor senses the various reflectance of the area region phenomena it observes. And about GIS, this is Geographical Information System. Some people would call it Geographical Information Science, or there are other names also, but we'll concentrate on your Geographical Information System. Now, when remote sensing produces data, and this remote sensing is remote, that means the data or the image or the reflectance or the intensity values are taken at a distance which is far off, not near. So the phenomena is observed from a distance, and when this remote sensing creates some data, and that data gives you some sort of way to go ahead, then GIS comes into play, and this data can be used. What remotely sense data imaging has given us, we can take this data and place it in GIS. GIS is a whole system of software, hardware, and then the humanware, and also finally the dataware. So this data which is there, which is remotely sensed, it is not at that position. Means you have to bring it to that level after geometrically correcting it. After a lot of correction is there of atmospheric correction, etc. Then this is spatially referenced, means that data just you can click through a camera, and that camera image is having no spatial reference. That means if you place it on a globe, it is not going to place anywhere. So GIS helps in doing that, and you can take a raw data, you can do the raster and vector activities with it, and then you can analyze it. So GIS is there for analysis of the data which is produced by remote sensing. And now GPS, because now we are talking about the spatial reference data. So spatial reference data means you need to know the locations. So location is very important as far as the data of our concern, that is remote sensing GIS people is concerned. That GPS is very important. So GPS is now, actually it was sent, or it was introduced for a specific reason, to help the military and to guide the defense services. But people have not thought, the department has not thought that GPS would be so incredible and so informative and so useful in every regime of life, that even our mobile has a GPS. Every car, everywhere you go, you'll find GPS. People are talking about GPS. GPS is a household name now, because remote sensing GIS may not be, but GPS is a household name just to know the locations, for navigation purpose, etc. So we'll talk about all these. We'll start with the remote sensing platform first. What is remote sensing? As I suggested, remote sensing is a technique, a science and technology of observing the phenomena of an object through a distance, that is with non-contact information. If it is taken, it is known as remote sensing. That is why the word remote is here. So you are remotely sensing it. So what you are sensing is, we'll see about that, what your sensing is. But first we'll see what are the platforms we are talking about. Because when you are remote sensing, that is sensing from a remote area, what remote can be? A remote can be ground-based. That means this is a place where you can place your sensor, which is somewhat above the normal surface level of the where you reside or where this is placed. So it is at a height, say a tank height. A tank height is, you can place your sensor here, and then you can take the imagery. You can sense the area which is in this purview, or that it has, the sensor has the limitation. A distance has to be there. So at that particular distance, it senses it. So this is a ground base. So not a wide coverage it will be there. And since every imaging will have some or the other of sort of distortions, we'll be taking that if time permits. The second idea is to do it through airplane based. Means this is an airplane, a kind of airplane where you have that those airplanes are specially designed, and you have remote sensing, sensors which are there, and this flight sequence is there. That flight is for a required region. This flight is being undertaken, and that area is being remotely sensed. So the distances are going up. See, these distances are going up, and then finally we reach to that satellites, and satellite based remotely sense platform, that is you are here and you are remotely sensing the earth, you are observing the earth through a remote area location, which is your satellite. And satellite can be of hundreds of kilometers. Normally if you are talking about a MEO satellite, then it goes from 500 to around 1500 kilometers. So most of the remote sensing satellites which we generally know, they are at around 8 to 900 kilometers from the Earth's surface. So we'll start with the satellite base because this is the most important. The first one, which is the ground base, is undertaken at a place which we want, that area is crowded, say, or it has some problem. So you sense it through that ground based sensing. But when it comes to an area of special choice and the area is limited, then you go to the aircraft based remote sensing. But when you want to cover a whole earth, that is, you want a global coverage of some sort, then you rely upon the satellite based. Though the initial amount or initial investment would be quite high to send a satellite, but once it is placed in the orbit, then it is going to give you worth of each penny you have spent. So this is the sun synchronous polar satellite, and this is how it moves. This is your globe. It moves like this in an elliptical orbit. So most Earth imaging satellites, they are polar orbiting, meaning that they circle the planet in a roughly north-south ellipse, while the Earth which revolves beneath them. Therefore, unless the satellite has some sort of pointing capability, there are only certain times when a particular place on the ground will be imaged. Say at 10:30 morning, it passes over Honolulu. Just take an example. Every time, every day at 10:30, you'll see the satellite for 15 to 20 minutes roundabout at this place. This is what this sun synchronous polar orbits is all about. So it has a global coverage. It has a fixed crossing, that this 10:30, and it has a repeat sampling. Means the revisit is also good. And the typical altitude, as I said, it is 500 to 1500 kilometers. For example, you have Terra, Aqua, Landsat, Spot. There are so many to name. We'll be covering that in later session. And then non-sun synchronized orbits are also there. These are tropics, mid latitudes, or high latitudes coverage, which is varying sampling, like 200 to 2000 kilometers. There are some satellites which move like this also. Then the geostationary satellite, which is almost covering the one third of the globe. And why it is important is that it has a regional coverage. Means one third of the earth they are going to cover. And why this is having a continuous sampling as opposed to the repeated sampling, since this satellite is at around 36,000 kilometers from the earth, and these are over low middle latitudes. These lower middle latitudes, and you would need around 3 geostationary if you want to cover the complete globe. But still, the polar area will be left somewhat unsensed actually. So there are two types of remote sensing. What the difference is, what we say that the difference is just in the sensing of sending or not sending. That means in both the cases the sensing is done, but in passive case the sensing is done with respect to or on the basis of some other natural phenomena. Means if sunlight is there, an object is subjected to the natural light always, or some other light, that light is been, or that reflection, absorption properties are being sensed from this sensor. And the sun, which is having a wavelength from the radiations from sun from 0.5 to 5 micrometer, and earth or its atmosphere, which is having the wavelength from 3 micrometer to 30 centimeter. So it is not sending anything. This sensor is not sending anything. It is just experiencing or just sensing that reflectance by the natural sources which are available on the earth, or available for us as a resident of this globe. What about active? Active remote sensing is like this, that you are sending the electromagnetic radiations from where you are, and that can be SAR, that can be other electromagnetic radiation. So mostly SAR is being done as SAR is being called as active. Also lidar is an active. So what we send here is the electromagnetic radiation at that synthetic aperture radar range. That is, you go to that CX band, and then you sense it back. So whatever you send, you sense it back. You don't rely upon the natural sources. So radar and lidar. Radar stands for radio detection and ranging, and LIDAR stand for light detection and ranging. And the radar has wavelength from millimeter to meter, while the LIDAR has the wavelength which we know, that is ultraviolet, visible and near infrared. So this is kind of active remote sensing. So just consider that a camera takes a photo. As example, if you are taking a flash, if you are using a flash, that means you are doing active remote sensing. If you are not using a flash, you are doing a passive remote sensing. So this is a remote sensing raster, because I need to tell you that what exactly you get out of when you remotely sense a particular area. Then for an instantaneous field of view, that is a area which satellite, because satellite is correct, is consisting of various array of detectors. So at particular time where the imaging is being done, that particular snapshot I am trying to tell you. So these are the reflectance value which are here. And see, the bands which we are talking about is in electromagnetic spectrum. You have various bands or various wavelengths. So if I am taking some say 0.4 to 0.5, then this is known as the first band. I am just taking an example. 0.5 to 0.6 is second band. Actually, it is not 0.4 to 0.5. You know, when it sends, it will go from 0.42 to 0.48 like this, because we have something called as we will see it in the resolution aspect, that actual wavelength sense, or actually region sense, is not that which we normally talk about in theory. So this is what we get. So these are the brightness value which we are getting, and brightness values are nothing but the numbers. How you are getting these numbers? Say you have a sensor which can sense that a radiometric resolution is 8-bit. So it can sense from 0 to 255. That is the value it senses will be either from 0 till 255. So these are the value which you see here. The type of resolution, there are 4 types of resolution basically, and these are spatial resolution, the spectral resolution, the radiometric resolution, and the temporal resolution. And I hope that these resolutions are well known to you if you are a remote sensing person. But let me in short give you an idea that spatial resolution, this is 80 by 80 image, this is 40 by 40, and this is say 320 by 320. Let me replace this, because this is not 80 by 80, this is 40 by 40, and this is 80 by 80. Okay, now 40 by 40 is not having that much information. It is not even pleasing to eyes, and 80 by 80 is showing something, but 320 by 320 is the actual view that our eyes see. But what is the spatial resolution? Spatial resolution is actually, this area. If this area is being seen at 1 meter, this area is being seen at 30 meter. The resolution says that you can very well identify the object. So spatial resolution is the property or is the capability of the sensor to discern 2 objects on the ground. That is the capability that to minimum level, or so you can say a pixel, in an image, what is the pixel size? That is your, in broad terms or layman language, a pixel size is your spatial resolution. So this is again an example of spatial resolution. You see 0.5 or 0.5 meter, how clear it is, and this is 80 by 80 meter. So what we are talking about here is instantaneous field of view and spatial resolution in large view. So you have 80 by 80. Then this one is, see, 5 meter by 5 meter. This is 5 meter 5 meter. And if you go this, if you are able to see this minute point, this is 0.5 by 0.5. So how clear it is. So this is your instantaneous field of view. This is the spatial resolution. What about the spectral resolution? Just examine this view. Now you are able to see an image, but you are not able to find out which color it is. Now spectral resolution helps in doing that. This is the property or the characteristics of the satellite or the sensor on the satellite. That is to how many wavelengths it is sensitive to. So intensity is the sum of intensity of all visible wavelengths. So this is just a black and white image, as you can see. But if I change it to different bands, you take red differently, green differently, blue differently, and you try to combine them in some or the other form, then you can get a very good image here. You can very well find out which colors are there. Then we come to the radiometric resolution. It is again the sensor sensitivity to the magnitude of the electromagnetic energy, and sensors' ability to discriminate very slight differences in the energy. So that is how many gray levels this radiometry, or how many gray levels sensor is able to provide. That is the ability to discrete very slight differences in the energy or the intensity or the gray levels. So finer the radiometric resolution of a sensor, the more sensitive it is to detect these small differences in the energy. Just for an example, this is a 2-bit image, And this 2-bit image, if I increase this 2-bit image radiometric resolution to 8 bits, so 2 to the power 2 is what? 4. So only 4, these are represented by 4 gray levels, 0 to 3. But now in 8-bit, we have 0 to 255. So this is more clear. So, we have gray levels which are varying from 0 to 255. So these are the basics of bit. See, these are the basics of bit as we talked about 8 bits. So it starts from 0 and it goes up to 255 actually. So this is 256 actually. And we can know that the bits decide maximum number of intensity differences which the image will have. So if it is a 12-bit image, the resolution is 12-bit image, the coverage would be, and the number of intensity partitions, the number of the image gray shades would be 0 to 4095. That is huge. So this is an Iconos 11-bit image which enables detail to be captured in the areas within the cloud shadow. And this is 8-bit image. There is not much detail, but in the case of 11 bits, you see in the black cloud shadow area image, this image shows improved shadow detail after some enhancement using full 11 bits. This is more clear. Then the temporal resolution and coverage, it is the property of the satellite actually. That is the revisit period. Since say at this place the satellite has come now. After 1 day it comes again. So we say that the revisit is 1. That is temporal resolution is 1 day. For example, Landsat needs 16 days. Modis needs 1 day. These are all various satellites. So temporal coverage is also very important because how often you can take an image of a place is important as far as the continuous sensing is concerned. So the application of temporal data, now we will come to the image analysis part, how to apply this in sensing. See, the urban sprawl means the area where the urban area has increased. So in 1973, it was this area. But in 1987, the urban sprawl has gone to an extent. So these area can be seen if we have a temporal data of different dates, different time. So application of remote sensing, because image, what we sense using the remote sensing, we can use image as the base maps first of all. And we can observe or measure properties or conditions of lands, oceans and atmosphere. And this maps spatial distribution of feature is there. There are spatial distribution of features like point, line, polygon. You can show your say a river, by a line. You can show a river even by a polygon. You can show your house by a point or even a polygon. So this record the spatial changes. Spatial means anything which is having a location information or anything which is related to the locations. This is a classification example if we take the supervised training. So now we have actually classified that this is a dormant grass, this is the bare field. So this is the actual image is there, and now we have applied, that is, we analyze this image with respect to the classification. And this is the classification result of what we have just seen. That all these legends, as you see, these orange one areas, they are showing the high density urban areas, while this blue one, they are depicting the water areas. The chain detection, that is the flooding. So Landsat imagery of a Mississippi flood at that time. This is your actual view taken by a camera, and this was again taken by a camera, but this is taken by the sensor of Landsat. See the area which it has covered. So it is more easy to analyze an image when you have these satellite images. This is quantifying the urban sprawl, how much urban sprawl has taken place. You can easily use this to measure the urban sprawl. Then the chain detection, this of urban sprawl of different area means how much urban area is increased in due course of time. So then monitoring the weather is also an important aspect of the remote sensing satellites. You can observe that what exactly is going on, and then you can you can analyze these images to find out what is going on, what will be there in future. And also detecting and monitoring wildland fires. This is the area because you can sense the heat, the IR imaging. So this is showing that these areas are affected by the fire. This is monitoring of sea surface temperature. If you have global coverage like geostationary satellite does take it, so you can observe the sea surface temperature of various places. This is also an analysis of the sea surface temperature. Then we have GOES and MODIS. They have 10 kilometer of spatial resolution, while the MODIS have 1 kilometer. And you can see what information does they provide, because MODIS and GOES, they are very important as far as various remote sensing and analysis agencies are concerned. So this GOES the temporal resolution is very good every hour, right? So that is why it is important, and this notice is giving a very good spatial resolution. Then we come to the digital elevation models. Elevation models are what? Digital elevation models are data files that contain the elevation of the terrain or a specified area using a fixed grid interval. As you have seen in the raster images, that you have intensity values here, but in digital elevation model you will have a height value here, or the elevation, or you can say the altitude. So this data file will contain the height value. So the intervals between each of the grid points will always be referenced to some geographical coordinate system. May it be latitude, longitude, that is the spherical version, that is your GCS, geographical coordinate system, or your UTM, planar system, or your state plane system. And the closer together these grid value are located, the more detailed information of the height variation you will be able to find out. And the detail of the peaks and valley in the terrain will be better model with a small grid spacing than with the grid spacing or intervals are very high. And there is always a distinction between DEMs and DTMs, because DEM means the digital elevation model, that is set of regularly or irregularly spaced height values. There is no other information, but DTM that has the globe also and the terrain also. So combinedly, if you combine terrain with the surface, then that is DTM. So digital terrain model, it is set of regularly or irregularly spaced height values, but with other information about the terrain surface also, like the ridges line, the spot heights, the troughs, the coast shoreline, the drainage lines, the faults, the peaks, the pits, and the passes. So this is an example of how digital elevation would look like. Then DM and TINs, that is your digital elevation model, can be represented in two forms. It can be in the sample points like this, height values or range values, or it can be in the form of TIN, that is triangle. These are the points. So you can combine or you can join 3 points to form a triangle, and these are the various triangles you can form. And these triangles, all these triangles has the property that this one triangle have all the points having the same altitude. All the points having the same altitude. This is a TIN based on sample points. And what are the extracts, or what are the outputs, what you can draw from a DEM? You can have or make a height map, you can make a aspect map or a slope map, or a hill shading means hill shading. If you want to observe that what our light is coming from sun at certain angle, which area is experiencing a shadow, that is hill shading. Then the plan curvature, the feature extraction can be done using DEM. There are other uses also, like this you can see, this is the digital elevation model, Red Rocks Amphitheater Colorado, obtained using UAV, and this is the Airfield 3D digital elevation model obtained using the UAV flying 200 above the hilltop. And the other uses are also there, that is the gate wing, or you can see these tunnels which are being closed. These are the model generators of the digital terrain model plus structure plus maps. And this is important ASTER. Why we are talking about ASTER? Because this is advanced space-bound thermal emission and reflection radiometer. And it was launched in 1999, and it was a part of NASA's EOS, along with the METI, Japan's J Space Systems, and METI, that is the Ministry of one wing. So the spatial resolution was 15 meter. It has around 15 bands. 15 bands are there, and resolution varied from 15 meter to 90 meter, and 16-day temporal resolution possible. But why we are talking about ASTER? This is important. Why we are talking about this ASTER is that the ASTER has provided the digital elevation model of complete globe. Complete globe, that is, it assumes 99% of the complete globe, that is the Earth. So this is why it is so important to us. And this is the we already said that radar also is used, and this is the active remote sensing. So this is a European ERS-1, European remote sensing satellite radar image of stormwater runoff plumes from the Los Angeles and San Gabriel rivers into the Los Angeles and Long Beach harbors. And as you see that the SAR is basically dependent on the reflection. So where the reflection is high, you will see this black area. Where it is less, or the images or electromagnetic radiations are not coming through the sensor, there will be a white area. Now we come to the geographical information system part. So what do we mean by geographical information system? The different parts we'll discuss just now. But before that, let me tell you that the geography, that is geo means earth. So anything related to earth, The information providing system is geographical information system. So information system are providing system which are providing information for the globe or the earth or the geography is known as the geographical information system. So the definition is GIS is a system of computer software, hardware and data and the personnel to help manipulate, analyze and present information that is tied to a special location. So what we are talking about here is the hardware plus the humanware plus the dataware plus the software. So you combine them and you'll get a geographical information system. Essentially, people talk about GIS as the software, but it is more than that. And why it is important is that whatever you have taken through remote sensing or any sort of imaging, you have the data. Now you want to analyze it. You want to place it in some system so that you can what you have acquired, you can ingest it, you can keep it, you can manipulate it, you can analyze it. Then if requirement comes, you can again represent it, or you can send it, or you can analyze the result, or you can extract the results also. So this is the special location, that is, we are talking about special location in the geographical information system. So any geographic location, anything, any point or any data which is having a geographic location or a spatial data, spatial location or a location on the earth is the spatial data. The information is the visualization or of analysis of data. And the system is the linking of software, hardware and data. And what about the personnel? The most critical key to the successful use of GIS is personnel, because we are the people who will be working on this GIS. So we need to be GIS expert, we need to be GIS starter or GIS analyst or a photo interpreter or anybody who is related to this field. For them, GIS is always there, and GIS helps to enhance the capability or to automate, and problem solving can be done more easily with using the GIS. And in GIS, the data is considered to be in the two forms, and the input to the data, or you can say the data structure of your GIS, is essentially regarded or categorized into broadly into two categories. One is your vector and one is your raster. Raster is what? See, this is your river. This is your river. How you are going to place it in raster? We'll place all R here. See, all R is representing that we have a river here. What about house? This is house. So we have two houses. So we placed H here, H here. What about trees? How many trees are there? 1, 2, 3, 4, 5. So T, 6 around there. One more will be there. So this is how we represent in raster the actual earth, actual objects or the living being or the natural resources which are present on the earth. So we are presenting it in the GIS in the form of raster. Then the real world we need to present it in the actuality. How does it look? So these are only points. These are only points, and this will not give you a realistic value, though it is very good. For certain operation it is very good, raster representation. I'm not drawing any differences between raster and vector in terms of which is good or bad. I'm just saying that raster and vector, they both have their presence and importance and usage in some or the other activity. So it will be good for somebody, may not be so well for the other person. So vector representation is the actual representation of how these point line polygons in the terms of point line polygon you can represent the earth, because this is what? This is your house. So you can represent it either as a point or as a polygon. And what this is your river. So you may use a continuous line to represent it. So this is point, and anything on the earth, point line polygon, can be represented by a point or a line of polygon. Anything can be represented in these three geometries. So this vector representation is the representation of the geometry. Raster representation is the gridded or the pixelated gridded equal distance or equal distribution values. Then what is spatial analysis? GIS helps in spatial analysis. What do we mean? Don't worry about this word, and actually it is quite confusing, spatial. You just understand this is spatial means anything which has latitude, longitude with it. Okay? Now this will be good for you, because it is not very easy to understand spatial. It is a different word. Now we'll be using this spatial again and again. What is this spatial? Spatial is related, it has come from space. Space means anything in the space, if you are able to locate it, you can point it, and that space is your globe, your earth, or even the celestial objects like your Mars or moon. So those spatial, the location of the point, any point, that is a spatial data. So data analysis transform data into useful information, and we are analyzing it only. We are interested in analysis. So the method of analysis is spatial if the results depend on the location of the entities being analyzed. So we can move the feature and result would change. or the analysis modifies the geometry or creates a new geometry. So these are the two ways in which we can do the spatial analysis. Let us see the proximity analysis, that is the buffering. What is this? We want to create a new area within a user-defined distance for an existing entity. For example, we want to determine the area which is impacted by a proposed highway. So this is a highway which we are trying to subsume, or we are trying to expect build. So this area which is in the shaded blue region, somewhat blue, this area is that area which is affected. So you need to take care of this area. So this is how, just by sitting at your desktop, you can plan and make decisions on the basis of this buffering. So this is the proximity analysis, one of the outputs of the GIS. So this is again a proximity analysis, a point. See, this is the proximity area. This is the proximity. The red region shows the proximity. If a line is there, this is the proximity. So this is how you find the proximity. So to find out the proximity, you take the distance, that is the gradient distance you take, and then you mark those area. You can have a variable distance buffer also. For example, if this is the example of 3 different proximity analysis. Means these are the rivers. These are the different rivers, and one river is shown, this one, with the buffer distance of 50 units. As you see, this rivers, they are showing the buffer region of the buffer distance 75 meter, while this broad region is showing the buffer region of, or the proximity analysis of 75 meter, 100 meter, sorry. Then the contiguity analysis. Now you would like to find out which states share a border with, say, one of the state of US, that is Missouri. This is a question of connectivity, and the proximity analysis of this is that all the areas or all the regions which are connected, that can be found out using GIS. So the neighborhood function is how you can get it. We can calculate an output value at a location from the value at nearby locations. You can use it by some moving window, or you can use range, mean, median, minimum, or maximum, or majority, aspect, slope. All these you can use to find the proximity analysis. For example, this is your input, say, pixel values or the values here. Then you can apply the neighborhood maximum, and this will be your final region. This is how you find out the neighborhood analysis. Then we finally come to the third topic of today, which is our global positioning system, or GPS. So GPS, it does stand for Global Positioning System. So it is a satellite-based navigation system to find the exact location, the latitude, longitude, even the height of your placement where you are placed. So it is a complete global system. That is, it gives you a location at your, say, small mobile or a gadget which you are going to see, just by getting some signals from the satellites which are located or orbiting at 20,000 kilometers. So how GPS work? We have around, if we talk about, say, the GPS, US GPS, which is initially called as Navstar GPS, or navigation, the ranging. So what exactly was there? Now we have around more than 50 satellites which they have sent. So 24 satellites are always revolving around the Earth. So for a position, for an individual at a certain location, he will have an excess of minimum of 4 satellites. He will always have 4 satellites which are watching him, or he is watching them. So he can log these 4 satellites, and these satellites, with the technique of trilateration, it gives you the exact position where you are there. It varies. There are various possibility because of PDOP, number of inaccuracies. There are number of possibilities. So you may get some accuracy to 10 to 20 meter, but there are ways also, real time or post processing, that you can get the exact location to sub centimeter accuracy. So how exactly this GPS work is? We have satellites, as I said, there are around 24 satellites that you are able to see. And let me tell you about India also. India, we have IRNSS, that is Indian Regional Navigation Satellite Systems. That is a regional satellite system, though right now it is using the GPS of US only. But once it gets that data, or that signals, it is able to provide the data to the individual, or the signal to the individual, so that he may get an accuracy of 1 to 3 meter. So IRNSS is a combined effort of ISRO and the airport, say aviation ministry, and they have come up with this IRNSS, which signals we have started, which we are getting, and the satellites which are sent is through GSATs. So these satellites have accurate, those satellites which we send on the revolution for GPS purpose. They have strong, accurate atomic clocks. Very accurate means in millions a year they will lose some nanometer, second. Nanosecond, sorry, not nanometer, but in millions of years they will lose just nanosecond. So still, satellites have accurate atomic clocks on board, and all GPS satellites, they transmit same time signal at the same time. That just assume that you are synchronizing your watch, or they all synchronize themselves. And see here, the satellite signal contains various aspects. That signal contains LM9 data they send in L1, L2, that is L band, and that is around 1555 and 1375 something. I may not be accurate, but the idea is this only. This is the megahertz. So this is the frequency at which they send, and this we have PA code, and this is the CA code and P code. CA is for course acquisition code, and P is for the private code. So we get, or we assume, or we get the data from CA code. The element data, I mean the position, the orientation, the angle, all those things is sent to the ground segments also, and it is sent to the receiver also. Now receiver can with knowing all these location of the satellites which are there, and of course knowing it's the fourth location. So if we have I have this diagram, so I'll just tell you. So receiver, they use the LMNet data. LMNet data, why we are calling LMNet? Because it is flooded with the information. So there are a lot of data which that satellite is sending. So that LMNet data may have the position of all satellites every second, and this is updated timely for control stations also. So this is not only for the satellites. There are a number of control stations that is called the ground segment of the GPS satellite, and that satellite is received compared with the receiver internal clock, and then if the time is sent, the position is there. How to know the distance, or how to know, because the time at which it was sent, the time it has reached. So we have this time, and with respect to time, and we know the speed of light is 3 into 10 to the power 8. So we use this time and velocity to find the range or the distance. We know the distance. Okay, so this is what? This is the radius of the sphere it is sending. Right? This is with the others also. So this trilateration we use, that is trilateration which finds out the exact location. We'll see about that trilateration. What is trilateration? So starting by determining distance between a GPS satellite and your position, where you are right now. You are here at certain position, right? So see, let me show you once again. Because where you are standing here is this location, right? Satellite is here, and you can be anywhere on the spherical area which that satellite is making. And then you add two more. One more is satellite is here, the other satellite is here. You are getting the information of that. So you can be anywhere in between. Then the third one can come. The third one is coming. So the third one says that you are at this position, maybe at this position. But one position will be good, one position will be very far off. But now you are not able to know. So for that, you can just take one and disregard the other. But if you have the fourth one also, see, the fourth one is actually giving you a very exact picture. The fourth one is giving you an exact picture. Now you have that point. So the fourth one, 1, 2, and 3, and the fourth one, say, this fourth one, it is giving you the exact location where you are. The sphere where they are actually intersecting, the fourth position, these are various satellites, will give you exact location. Fourth will give you a height also. See, this is the how it is taking place. You have 4 satellites, and this is the point, is the final intersection of these 4 spheres, virtual sphere they are making, and this is the exact location. This is called the determining GPS position trilateration. Then you have GPS receivers. So these are the kind of GPS receivers. You have handheld GPS receivers. You can place it somewhere stationary. You have differential GPS. So various GPS. See, this is the differential GPS. There are various GPS which are present. And let me give you an idea of differential GPS. What it means is you are here and getting information. Now you have accuracy, say from 10 to 20 meter accuracy is there. So you want an exact location. So what happens here? That there is a ground segment. Now this location is exactly known. there is a ground segment which you can interact, and this has the exact location. It knows its location. So when it receives the data from the satellite, alarm data, say it is getting X position, and it knows its position is Y. So the difference is Y minus X. It knows that this Y minus X is the error which this satellite is right now generating, and this difference is sent to the individual receiver, and that is adjusted, and then you can get the sub-centimeter level accuracy. This is the power of GPS and the differential GPS. There are various satellite navigation systems in use, and various states of development they have. GLONASS first is because GPS we have known, GPS we have known. Let us talk about GLONASS. This is Russia's global navigation system. See, one is global navigation system, so it is covering complete globe, and there are regional navigation system, that is those which are only covering a region. So we'll differentiate between these. GLONASS is the Russia's global navigation system. It is fully operational worldwide as the GPS, which we have talked about in greater length by now. And this GLONASS is the global navigation system by Russia. Galileo is the global system being developed by the European Union and other partner countries, and it is operational right now 2016, and it will be fully deployed by 2020. So it is you can say a European Union satellite navigation system. So after this we have Baidu. What is this Baidu? Baidu is your Chinese. See, this is your Chinese navigation system, and this is the Chinese regional navigation system. This is your regional navigation system. Okay, it is just related to your particular area that China is doing. But we have Compass coming up. This is China's global system, and it will be operational by 2020. IRNSS, this is our India's regional navigation system covering the India and North Indian region. And QZSS is what? This is the Japanese. See, this is Japanese regional system. So it is covering only the regional coverage of Japan. So thank you so much. We have just taken the three important topics of the area. The area is so wide, and these three technologies, they come together for a remote sensing GIS person, and this gives you the exact information and the power of how to create information for the betterment of the society, for better decision making, and how to help others using and employing your knowledge of these three important topics. Thank you so much. Take care of yourself.